asking the impossible. The Big Bang is often described as the beginning of everything, of space, time, matter, and energy. It is the cosmic drumbeat that launched the universe we see today. Yet even as we trace the galaxies racing apart, the background radiation is still humming from those early moments, and the abundance of hydrogen and helium forged in the fires of the first seconds, a deeper question lingers. What came before? At first glance, it seems like a natural question, as intuitive as asking what lies beyond the horizon or what happened yesterday. But with the Big Bang, we quickly run into a problem. Time itself is thought to have begun with that event. There was no yesterday, no earlier moment ticking away. There may have been no ticking at all. Space and time are inseparable, at least in this universe, package pair, and asking what's before this universe, much like asking what's outside the universe, gets problematic and non-intuitive. In fact, the answer to both might be nothing. To ask what came before the Big Bang might be like asking what's north of the North Pole, a question that dissolves not because the answer is hidden from us, but because it has no meaning within the framework we understand. You can still go further up or sideways, rising off the planet, but that's not further north, just up. And similarly, even if there is more beyond or before this universe, it might be that time and space do not apply, same as left or right don't mean anything in the context of planetary directions like north, east, south, or west. Still, we are human, curious to the core, and ever defiant of boundaries, even those drawn by physics. So today, we'll explore the frontier beyond the final frontier. We'll ask not only what could have come before the Big Bang, but whether that question itself needs to be reimagined, and we'll tour the many scientific theories that attempt, each in their own way, to pull back the ultimate cosmic curtain. The limits of time and space-time. In the earliest moments of the universe, so early that calling them moments already feels misleading, our current physics gives way. General relativity, which so beautifully depicts the curvature of space-time, predicts a singularity, a point where densities and temperatures become infinite and the laws of physics break down, much they are thought to do at the center of black holes. But infinities are suspicious creatures. When they pop up in physical equations, it's usually a sign we're pushing a theory beyond its limits. Many physicists today argue that the singularity is not a physical reality, but a placeholder for where our understanding fails, and I tend to agree. More intriguingly, general relativity suggests that time itself is not a backdrop against which things happen, but a property that emerges with space-time. If space-time was born at the Big Bang, so too was time. Without space, without matter and energy to interact, what would the ticking of a clock even mean? This leads to ideas like the no-boundary proposal, developed by Stephen Hawking and James Hartle. Rather than a singular point where everything began, they envisioned the early universe as finite but without a boundary, much like the surface of a sphere has no edge. But there's a deeper twist. Near the Big Bang, time itself is thought to lose its familiar meaning. In Hawking and Hartle's model, the early universe can be described as using imaginary time, where time behaves more like a spatial dimension. In everyday 3D space, we calculate distance using the Pythagorean theorem. The distance squared is the sum of the squares of the differences in the x, y, and z directions, up, down, left, right, forward, back. We move this into space-time by having a space-time interval, where time gets turned into a kind of distance, the causal distance being the time interval multiplied by the speed of light, how far light would travel in that period. We square this, but instead of adding it to the squares of the spatial distances, up, down, left, right, forward, back, we subtract it. That's the normal approach in special relativity, and it reflects how high relative velocities or strong gravities tend to either shrink distances or stretch out the local passage of time. In imaginary time, we take time coordinates and multiply it by the imaginary unit I, the square root of -1. When we square this, it flips the negative sign, effectively adding the time term instead of subtracting it. The result is a more familiar four-dimensional distance formula, where time and space are treated alike. That's why in imaginary time, time behaves more like a spatial dimension. It sounds technical and mysterious, probably because a lot of people explaining it seem to aim for that, but it's really not. Instead of flowing from past to future, in this framework, time becomes just another direction you can move through, indistinguishable from the directions of space. In this view, the universe near its beginning is shaped like a four-dimensional hypersphere, finite but unbounded, and the sharp distinction between time and space only emerges as the universe expands and cools, effectively four physical dimensions and no temporal one. So again, asking what came before the Big Bang then becomes as meaningless as asking what's north of the North Pole. But here, it's not a 3D sphere we're talking about, it's a 4D one, and there's no sharp corners or holes for singularity. It is an elegant solution, replacing a problematic singularity with a softer, rounded start. But not everyone is satisfied. It may explain why time doesn't extend backward before the Big Bang, but it leaves open the deeper mystery of whether something more fundamental gave rise to spacetime itself, a mystery that theories of quantum gravity are still struggling to solve. Imaginary time is also used in Euclidean quantum gravity. We'll bypass discussing what a Wick rotation is and why it's handy in quantum, but the justification here is that we can maybe switch over to using imaginary time in the ultra-early universe because of how incredibly dense it was and how sharp the curvature of spacetime would be. In the earliest moments of the universe, the first force to emerge was gravity, and when it was doing that, we were definitely in the realm of quantum gravity, due to the tiny space and massive energy scales, and we don't really understand quantum gravity yet and have many competing and less than compelling theories for that. You also have serious causality issues with using imaginary time, but at the beginning of time and at the quantum level, you pretty much have these anyway. So again, elegant but does suffer from some big issues. You might be trying to figure out what imaginary time is in a physical context. If so, do not waste your time. The answer is it hasn't got one. Imaginary time is a mathematical method. There's no such thing as an imaginary second in the physical world. Imaginary numbers extend math beyond the real, but -1 still has no physical square root, and there is no imaginary second or year. Beyond the Big Bang, alternate beginnings. If the Big Bang wasn't truly the beginning, what could have come before? In the search for answers, physicists have looked beyond the familiar landscape of particles and fields to more fundamental terrain, where space and time themselves might not yet exist, or where they exist in radically different forms. One of the earliest and most intriguing ideas comes from string theory. See our episode on string theory for a deeper dive of the topic. In this framework, the basic building blocks of reality are not point-like particles, but tiny vibrating strings of energy. Each vibration mode corresponds to a different particle, much like various notes a violin can produce. But for mathematics to work, string theory requires extra dimensions, beyond the theory of space and what of time we experience. Enter string gas cosmology, an idea proposed by Gabriel Veneziano and colleagues. Here, the early universe wasn't a smooth, empty void, it was a dense, hot gas of strings. In this primordial state, space was tightly wound, compacted into tiny loops, perhaps as small as the Planck length, 10 to the negative 35 meters. Time, as we know it, did not yet exist. Instead, the universe was a kind of quasi-static equilibrium, a timeless sea of quantum chaos. Over time, if time even applied, some of the spatial dimensions began to expand, while others remained curled up, giving rise to the four-dimensional spacetime we inhabit today. In this view, the Big Bang wasn't the beginning, it was a phase transition, and a potentially local one, our universe erupting from this wider ocean. Like water freezing into ice or steam condensing into water, the universe shifted from one state of existence to another. From a tangled thicket of vibrating strings emerged the smooth fabric of space-time. Other models in string theory paint an even grander picture. In pre-Big Bang cosmology, inspired by the works of Veneziano and others, the universe started in a state dominated by gravitational waves and dilations, exotic fields predicted by string theory. Instead of a singularity, there is a mere symmetric bounce. The universe contracts in one phase and then smoothly transitions into expansion, flipping the arrow of time along the way. If such a bounce occurred, the universe could have an infinite past, a prehistory stretching backward forever, though with conditions so alien they defy easy description. Space and time, in their pre-Big Bang forms, might not resemble anything we recognize. Some even propose that our universe is but a bubble in a grander cosmic foam. Bubble nucleation is a feature of certain inflationary models, particularly eternal inflation, where the underlying vacuum, called the more fundamental reality, is unstable and regions of it occasionally pop into lower energy states, forming new universes. Each of these bubbles expands, potentially colliding with others, creating a vast multiverse of pocket universes, each with its own laws of physics. If that's the case, the Big Bang we know and study was merely the local beginning of our bubble, not of existence itself. This leads to a tantalizing possibility: bubble collisions. If another bubble universe collided with ours early in its history, it could leave behind scars, subtle imprints in the cosmic microwave background, the faint afterglow of the Big Bang. Some scientists have searched for such patterns, circular anomalies, telltale disturbances that might whisper of ancient cosmic collisions. So far, nothing definitive has been found, but the search continues, and this is a very positive aspect of this particular theory, as most of our notions of time and space beyond or before our own universe tend to have no way for us to collect evidence of them, which is obviously problematic for science. We have many radical ideas about cosmology, many awesome, but without evidence, even if true, an idea is all they can really be. Here's another radical idea. What if our universe was born inside a black hole? Some theories suggest that black holes may not end in singularities, but instead connect to new regions of space-time, essentially birthing new universes. This notion is very parallel to wormhole concepts, only here it is connecting to another universe, not elsewhere in this one, which conveniently gets around the causality-violating problems that come with faster-than-light motion and time travel. In this model, every black hole could be a portal to a baby universe, and perhaps our own universe was born in such a fashion. The inside of a black hole formed in some parent cosmos. Time, inside a black hole, behaves very differently. Space and time may even switch roles near the singularity. This could, in principle, allow for a kind of cosmic rebirth, a universe within a universe. Needless to say, if every black hole births a new universe, then ours may be descended from one in another universe, and that one from yet another, black holes all the way up and down. You might be wondering if that implies there's a gateway somewhere in our universe we could enter, but you would not expect to find one. That gateway would have been the Big Bang itself, the very moment our universe was born. And going upstream, that's not likely to end well. There's no portal in our cosmos that lets you leap into a parent universe. Even if you could enter a black hole, remember that from the outside, it's essentially a moment of ultra-slow time. Emerging on the other side, if it's even possible, might not happen until that black hole evaporates, trillions upon trillions of years from now, when the universe is long cold and dead. All that remains are black holes, around which civilizations might still flourish, but they may pass through them into new universes and new Big Bangs somehow. If it remains a theory, it would be the ultimate leap of faith. Or consider white holes, theoretical opposites of black holes. Instead of swallowing matter and energy, a white hole expels it. Some models suggest the Big Bang could be interpreted as the ultimate white hole event, the sudden explosive eruption of space, time, and energy from a prior, hidden state. Of course, these ideas remain speculative, again fascinating but difficult to test, yet they offer us something precious, a way to think beyond the traditional story, to imagine a cosmos not bounded by a single moment of creation, but woven from layers of deeper reality. At its heart, these theories challenge our assumptions about time, causality, and existence itself. If the Big Bang was not the beginning, then what we see around us, galaxies wheeling through space, stars burning, planets spinning, is but a chapter in a much larger and more ancient story. And as we dig deeper, we find that even the notion of time, the most basic of experiences, may not be as fundamental as we once thought. Other realities, higher dimensions, and shadow universes. As we dig deeper into the question of what might have preceded or transcended the Big Bang, we quickly find ourselves wandering into the strange landscape of higher dimensional theories. These ideas suggest that our universe is not the whole of existence, but merely a slice, our brain, embedded in a larger, richer reality. In brain cosmology, derived from string theory and its offshoot M-theory, our universe exists on a three-dimensional membrane or brain floating within a higher dimensional bulk. Think of a sheet of paper suspended in a vast invisible space. There could be many such brains, each representing a separate universe, parallel to our own, perhaps mere millimeters away along a hidden dimension, but forever out of reach. In some models, the Big Bang itself might have been caused by a collision between brains. When two brains collide, the immense energy of the impact could ignite a new universe, ours. This is the foundation of the ekpyrotic model, which we touched on in earlier episodes, but it extends further. If brain collisions are common, then Big Bang-like events could happen repeatedly across the bulk, giving rise to countless universes. Each would have its own distinct properties, its own version of physics. In such a reality, the Big Bang is a localized event, a kind of cosmic fender bender, rather than a unique creation moment. The larger bulk continues on, perhaps eternal, with brains drifting, colliding, and birthing universes in an endless, higher dimensional ballet. Adding to this weirdness is the holographic principle, an idea born from the study of black holes. Proposed by Gerard 't Hooft and Leonard Susskind, the holographic principle suggests that all information contained within a volume of space can be described by information encoded on its boundary, much like a hologram, where a two-dimensional surface can create the illusion of a three-dimensional depth. Some physicists have speculated that our entire universe might be a holographic projection from a distant two-dimensional boundary. If so, the three dimensions we experience, length, width, height, and even time itself, could be emergent phenomena, shadows cast by deeper, more fundamental processes occurring on a cosmic screen. In this view, the Big Bang isn't the birth of space and time, but the moment when projection began, when the information encoded on the boundary coalesced into the illusion of a universe. What existed before this moment might not involve space or time at all, but rather a deeper, timeless informational substrate. It's an unsettling thought. We tend to think of reality as something concrete, solid, and three-dimensional. But if the holographic principle holds true at cosmic scales, reality itself might be more ephemeral than we ever imagined, a grand illusion stitched together from the quantum foam. Taking things even further, we can imagine shadow universes, higher dimensional realms that cast projections into our own, influencing the universe in ways we barely detect. Some have speculated that dark matter, the mysterious, invisible mass that outweighs ordinary matter 5 to 1, could be the gravitational influence of matter existing on another brain. It does not interact with light or ordinary matter except via gravity, making it virtually undetectable except by the pull-on galaxies and cosmic structures. Could it be that we are already feeling the gravitational tug of other universes whispering across the bulk? If so, then the Big Bang may not be a singular origin event, but merely a flashpoint, a localized manifestation in a much grander, interconnected tapestry of realities. Today we're wrapping up our third episode, deep diving the mysterious high-energy event we call the Big Bang, and its variations and alternative theories. And if you're interested in more mysterious and high-energy action out there among the stars, Nebula's original sci-fi audio drama, The Sojourn, is a brilliant companion. It follows privateer Captain Cassandra Farron and Dr. Elizabeth Anslet as they navigate fragile alliances, internal divisions, and a ruthless alien adversary, all set in a richly imagined universe that feels part Age of Sail, part hard science fiction. It's brought to life through veteran voice actors, immersive sound, and an epic original score. For us to reach out to the stars and settle the galaxy, we'll need some impressive space infrastructure and the materials to build it, and in my latest Nebula exclusive, Mass Drivers on the Moon, we look at how colossal electromagnetic catapults could transform the Moon into humanity's first true off-world freight hub. By launching millions of tons of lunar rock into orbit, we might finally build the habitats, power stations, and megastructures needed to break the grip of scarcity and set the stage for humanity to venture even deeper into the cosmos. You can watch Mass Drivers on the Moon, The Sojourn, and every episode of this show early and ad-free on Nebula. Get a lifetime membership for just $300 and unlock everything forever. Or start with an annual plan for only $36. That's a full 40% off. Head to go.nebula.tv/IsaacArthur to join us and keep exploring the biggest questions of time, space, and everything beyond. Emergent Time. We take time for granted. Seconds tick by, days pass, civilizations rise and fall. What if time is not a fundamental part of the universe? What if it's more like a byproduct, something that emerges from deeper, timeless laws? This radical idea has been gaining traction among physicists searching for a theory of quantum gravity, the long-sought unification of general relativity and quantum mechanics. In these efforts, time is not assumed to be a basic ingredient of reality, but rather something that emerges under certain conditions, much like how temperature emerges from the random motion of molecules in a gas. One promising approach is causal dynamical triangulation, CDT. Here, spacetime is not smooth and continuous, but built from discrete, fundamental units, tiny building blocks, much like pixels on a screen or the atoms in a crystal lattice. These building blocks are not arranged randomly. They are stitched together following strict causal rules, meaning that cause and effect relationships must be preserved. As more and more blocks are added, spacetime as we know it, with its familiar flowing times, emerges naturally. In this framework, the universe in its earliest moments didn't have time in any familiar sense. Instead, there was a frothy sea of pre-geometric elements, a quantum foam out of which space and time condensed, like ice forming from supercooled water. Time, then, is not the stage on which the universe plays out. It's part of the scenery that emerges when the underlying rules are satisfied. A related approach, causal set theory, takes the idea even further. It posits the fabric of the universe is made up of a growing network of discrete events, connected by causal relationships between them. There's no continuous space-time underneath it all, only a web of what can influence what. In this view, space-time is more like a social network than a smooth canvas. With each event linked to others, it could causally affect or be affected by. Here, before and after are emergent concepts, not fundamental ones. The universe grows, event by event, much like a tree branching out. The arrow of time, the fact that we remember the past but not the future, could itself be a consequence of this growth process. These models imply that the Big Bang wasn't the birth of time, but the beginning of its emergence. Before that, there was no ticking clock, no past or future, only a timeless, pre-geometric state, pregnant with potential but empty of what we would recognize as moments or memories. More speculative still are ideas from entropic gravity, where gravity itself, and perhaps time along with it, is not a fundamental force, but an emergent phenomena arising from the statistical behavior of microscopic degrees of freedom. Just as the pressure of a gas emerges from the collective motion of molecules, gravity and time might emerge from the information encoded in quantum fields at the very edges of space. If this is true, then time might not have a before or after outside of the emergent universe. Asking what happened before the Big Bang would be like asking what happened before temperature, a category error where the question dissolves once you understand the underlying reality. In this picture, the universe didn't begin at a specific moment in time. It began when time itself began to exist as an emergent property of deeper, timeless laws. These are not easy ideas to wrap our heads around. They defy our everyday experiences and challenge the way we've always thought about reality. But the universe doesn't owe us comfort or familiarity. If time is emergent, then so is history, and the true prelude to the Big Bang may be forever beyond the reach of clocks and calendars, a mystery written to a language without tenses or ticking seconds. Bubble collisions and multiverse scars. If our universe is not the whole of existence, but just one bubble in a vast multiverse, then it may not be as isolated as we imagine. In some versions of eternal inflation, new universes are constantly budding off, like bubbles forming and separating in a pot of boiling water. Each bubble could be a distinct universe with its own laws of physics, its own constants and structures, perhaps even its own versions of time and space. But bubbles do not always stay neatly apart. In the frothy chaos of eternal inflation, Bubble collisions are not only possible, they are inevitable. If two bubble universes collide, the results could be catastrophic for anything caught in the crossfire, but from safe distance, the evidence might remain, imprinted on the cosmic microwave background, the faint afterglow of the Big Bang. As we said earlier, some theorists have proposed that we might detect these collisions as subtle anomalies, slight circular scars in the otherwise smooth temperature map of the CMB, tiny cold or hot spots where another universe grazed ours in the early moments of cosmic history. To date, searches for such signatures have turned up nothing conclusive, but the possibility remains tantalizing. If we ever found solid evidence of a bubble collision, it would be proof not just that other universes exist, but they've already touched ours, cosmic neighbors brushing against each other in the earliest epochs. And if our bubble collided once, could it collide again? Could new universes be budding nearby, expanding rapidly and waiting to make contact? The multiverse, if it exists, might be far more dynamic and far more dangerous than we can currently imagine. Even without direct evidence, the idea has profound implications. It reframes the Big Bang not as an absolute beginning, but as a local event, a spark in a vast inflating sea. What we think of as everything may just be a ripple on a much larger ocean. Conclusion. What came before time? So, what came before the Big Bang? Maybe nothing, not in the sense we understand. Maybe time itself was born in that moment, rising from a timeless foam of quantum possibilities. Maybe the Big Bang was the product of a brain collision, a bubble forming in a higher dimensional bulk, or a phase change in some deeper, hidden reality. Maybe our universe is a holographic projection, a shadow cast by more fundamental laws we've only glimpsed. Or perhaps the real answer is stranger still, beyond our current theories, waiting for a new revolution in physics. What is clear is that the Big Bang is not the end of inquiry, it is the beginning. Very appropriately, a gateway, not a wall. A moment that invites us to ask deeper questions about reality, time, and existence itself. And if the Big Bang was not the first moment, if there was a before, we may someday discover it. Until then, we can marvel at the fact that we were even able to ask the question. Standing here billions of years later on the shore of time, peering into the darkness before the dawn.